Hi, good morning. Today is July the 10th, year 2012. Okay, so my talk will be 25 minutes, including the 5 minutes question and answer session. Okay, welcome to the session 2, and we'll start with the presentation on the dissecting power of regular languages by Tomoyuki Yamakami and Yuichi Kato. Okay, well, thanks a lot. Today, I'm going to talk about the dissecting powers in regular languages. This is about the formal language and automata theory. That topic will be this is the only one else on that topic in this workshop. So just to relax, and I'm going to introduce a new notion called detectability. So this is actually a very simple structural property for the languages. Particularly, I'm going to apply this notion to regular languages here. And throughout this talk, I'm going to draw attention of all of you to this particular notion. And also, I want to seek some sort of correlation. Well, the talk does not include much result, a deep result. It's just, I just skim over the surface of the notion. And now I'm looking for an international collaboration to solve a number of the questions, interesting questions that will be described at the end of this talk. So I start with the very basics of this new notion. I just remind you the basic model of the computation. I'm going to use two different models. The one of these is just a one-way, one-hit finite automaton. So the automaton is equipped with the infinite read-only tape, and an input is marked by the two end markers. And CPU and the tape heads move from the left end marker to the right end marker. And then they actually change the inner state to make a decision at the very end. Another model that I'm going to use is the finite automata that is equipped with the memory device called the stack. So at the same time, I'm going to use a non-deterministic computation instead of the deterministic one. So now I'm kind of ignores the finite portion of the infinite set. It's the most part of this talk is about the infinite set. And then we just simply ignore the finite portion of it. So to do so, I'm going to introduce two particular notation here. So this vertical line stands for the cardinality of the set. So this notation said the set A is a finite set. Well, instead of this one, equality is used. Whenever equality is used, this means the A is an infinite set. Because the language itself is a countable set, so that we don't need to worry about the many different kinds of infinite sets. Here, we will use the simplified notation like this one here. So AE stands for almost everywhere. So that this is, A is almost everywhere included in B. The picture here shows the exact situation here. A may not be included within B, but just cut off the finite portion of it. Then A might possibly be in B. And the equality sign here represents the both two inclusions happened at the same time. So well, throughout this talk, I'm going to use the following type of language families or complexity classes. The first one is the regular languages, the set of irregular languages, and the set of context-free languages. And the complement of the context-free languages is written as co-CFL. And the bracketed notation and subscript notation here are quite different. The bracket notation here, it's the CFL of L, of K, stands for the K disjunctive closure of CFL. That means that just take the K set context-free languages and then take the intersection of all of them. So that's the CFL of K. And the CFL sub K forms a Boolean hierarchy over CFL. And that is defined in this way, using the intersection and the union here in the even level and odd level. So, particularly, I'm interested in the structural property rather than the different kind of properties. Well, regular language, context-free language, those concepts are very old, and a lot of papers actually discuss a lot of different properties. But here, we are interested in structural kind of properties, and those structural things are actually discussed in the past literature. For example, the Boolean closure property, that is discussed in the 1960s, and the same linearity by Parikh in 1961, and minimum cover, it's a very recent one, and immunity or pseudo-randomness. So here we are going to introduce another kind of structural property called dissectability here. Dissecting roughly means that we can partition or split the infinite set S into two segments, here and here. And both sides have to be infinite. So it's very simple. So if you have one big infinite set, we just split into two infinite subsets. So how to dissect it? We just take the one language, it's C, and the complement of C. And C actually split this big infinite set S. So in that particular case, we will say that C dissects S. It's very simple. Nothing else. We will see it in two examples here. So one example is one non-regular language. This is an A to the n, B to the n, and a very typical example as appearing in many textbooks. So think about it, the set language C sub 1 to be the collection of the string x, and whose length is equal to 0 modulo 4. So this actually is split in S1. And another example might be the non-context-free language, WW, the strings of the form of WW. Well, C1 also dissects S2, but there's another one, a much simpler one, 0x. X is an arbitrary string here. So this also dissects S2. So the dissecting concept is very simple. And sometimes, like if you look at it as a concept like this one here, it's an S2 and the C2. C2 has basically no structure, but the first letter 0, that actually to contribute to to split S2 into two infinite portions. Now we'll expand this notion into more the capable notion here. So the F, the capital letter F, stands for some arbitrary language boundaries. And we will say F dissectable. The infinite language S is called an F dissectable if there is a language C that dissects S, and C belongs to F. So the important thing is the choice of F. For example, we can take possibly, say, P, the deterministic polynomial time complexity class. But this case is not really interesting, as we see. So we'll eventually take the F to be the set of regular languages. But why P is not so interesting? Because we can easily prove that every infinite recursive language or computable language is P dissectable. P is too powerful. The proof goes like this one here. Suppose L is an infinite recursive language. And then we consider it in two different cases. If L is almost everywhere equal to sigma star, then we take this one here as before. This dissect L. But then if L is not almost everywhere equal to sigma star, then first enumerate all strings in the sigma star. Then following this procedure to determine set C. So the procedure takes only polynomial time, and then as a result, the C is in P. And also here, I'm not going into detail, but if you use a simple diagonalization argument, we can show that C intersect L and the C complement intersect L. Two portions are actually infinite. So in the conclusion, is every recursive set, recursive language is P-dissectable. So, well, we don't have much room to explore as far as we are using P-dissectability. So instead of using P-dissectability, we may possibly restrict our interest into much lower complexity classes, like regular set. So now we'll take a quick look at what kind of language or sets are regular dissectable. The first one is the language called constantly growing. This notion is, it's a very simple language. And the language is called constantly growing if there is a constant P and a finite subset K of positive integers that satisfy the following length condition. So take any string x of certain length. Then we can always find string y such that the length of y is equal to length of x minus c, and the c is taken from this finite set k. So that we can always find a little smaller string within this L. So why this constantly growing language is important? Because we can show that the infinite constantly growing language is regular dissectable. The proof goes like this one here. If you look at the arbitrary infinite constantly growing language, L with constant P and infinite finite set K, and this K is enumerated in increasing order, then consider L sub I. So L sub I is the portion of L defined in this way, right? The length of x is equal to I modular C sub m plus 1. The C sub m is the biggest number in this K. And then we can easily prove that there are at least two indices, say I sub 1, I sub 2, and that such that the L sub I1 and L sub I2, both sets are actually infinite. So we just simply take one index and then define this one here. So this language completely dissect original language L. And of course, if you look at the definition of C, C is regular. So using this, it's a very simple observation. We can prove that the context-free language is also regularly dissectable. The proof goes like this one. Just observe that every context-free language is constantly growing, because we know that constantly growing language is regular dissectable. So we didn't claim. So what about the complement of CFL? So the co-CFL. So well, take a look at it, for example, the Fisher's language. So this is the n repetition of A to the n b. This belongs to complement of CFL, so co-CFL. For this particular language, for example, we can define C to be the string of x, whose in which the number of b appearing there is even. So that we have an even number of b's in x. So C actually dissect L. Because then, well, then L can be written in this way. So that either N is even or odd, right? So if you just take a look at the definition here, then, we can obtain this. So far, we have observed that that certain type of languages are regular dissectable. Is there any non-regular dissectable language? There is. For example, if you look at the logarithmic, deterministically logarithmic space bounded complexity class L, so L is actually not regular dissectable. The example languages like this one here, S to the a string of this form, 0 to the n factorial over, this is a unary language defined over the unary alphabet, 0. So we can prove that S is in L. So that in the logarithmic space, we can actually accept this string. And also, no regular language dissect this S. So by the argument is not that difficult. Assuming that we have a regular language that dissect S, then we just simply get the contradiction. So we move on to different kinds of languages called bounded languages. This notion was introduced by Ginsberg and Spanier in 1966, so it's an old notion. The language is called bounded if L has this form. T1 up to Tk are finite set of strings. So the example is like this one here, A to the I, B to the I, C to the J. For example, if you take the A1 for T1, B for T2, C for T3, then the definition, well, this satisfies this definition. And the second case, we take those assignment, then we'll get bounded language like this one. So what we are going to prove here is that the BCFLK, so this is actually restricted form of CFLK. All the languages are restricted to bounded. Now we can claim that BCFLK is regular dissectable. The proof is not that hard. Using the basically the proof is based on Ginsberg's characterization of the bounded context-free languages in terms of the semi-regularity. The semi-regular sets are defined by Tariq. And another example is the BCFL sub k. So this is the bounded version of the CFL sub k. And whole entire Boolean hierarchy is specified by the BCFL sub BH. The BH stands for the Boolean hierarchy. And this Boolean hierarchy over the BCFL is regular dissectable. The argument is quite simple and using the induction on the level k here. The first level is very similar to the case of the BCFL of n. And for induction step, we use the property of the Boolean operation in the even level and the odd level. So finally, I'll show you one application of regular dissectability. The why dissectability is kind of very important because we can actually prove something slightly different. So we will introduce the notion of the separation with infinite margins. The first one I will define the notion here is a set A covers B with an infinite margin. Well, the terminology is slightly long, so I'll just make a shorter version here. So A is an I cover of B, or I covers B. So I stands for an infinite margin, like an iPhone and stuff. So, yeah, well, actually, yeah, that's true. But so when AI covers B, then the B is a subset of A. As you see in this picture here, so A actually includes B, and the margin between A and B, so this area is actually infinite, right? So in this particular case, we said an AI covers B, and what we use in another notation that specifies an AI covering B is that B comma A. So be careful about the ordering here. The B is a smaller one and A is a bigger one. Yeah. And now we introduce the separation notion here. A set C separates B comma A. So this is the AI covering B with infinite margins. So in this picture here, it's an AI covers B, but now the C actually split between this A and B. And the margin here, then A minus B and C minus B, then the two margins are both infinite. Right? So that is actually specified here. And to state the result, so now I'll expand the language into language families in the following way. So we simply collect the pair of B and A to make this notation here. B is taken from D, and A is taken from C here. And language family, or complexity class E, I separate D comma C if every pair of B and A taken from D comma C, so we can always find a set that I separate this pair. And this set has to be taken from E. So that, in this picture here, if you take any I covering pair, A and B, then we can always find C from E that I separate A and B. So what is the relationship between the dissectability and the separation? So here is a claim here. Suppose C minus D. So this is the complexity class C and complexity class D, and this is the collection of the difference from the set from language from C minus language from D. So this complexity class is regular dissectable. So this is our assumption. Then the class defined in this way is I separate D comma C. Here is slightly complex, but this is actually needed if you look at the proof following here. Suppose we have an A and B taken from C and D respectively, and then make the D to be A minus B. And assuming that D is infinite, then we can always find C, regular set C, because assumption of the dissectability here, so that C dissects D. So now we define set E, so that actually appeared in here. So that this set belongs to E by definition. And dissectability implies, by a simple calculation, that this set and this set are both infinite. So using this, using the choice here, then we can actually prove this one here. And this clearly state that E, so this set E, I separates B comma A. So now we'll state the separation result. BCFLK, I separate BCFLK comma BCFLK for every level K. The proof is following the previous claim that well, to prove this one, we simply prove that BCFLK minus BCFLK is regular dissectable. This automatically implies that the BCFLK, I separate this pair, right? But here, this one is actually proven by the induction of K, so it's not that hard. So now, as I promised, and at the very end of the talk, and I'm going to explain open problems that have to be resolved on the due course of in the due course of the investigation of this very simple structure property. During the talk, I only mentioned about it in one particular example that belongs to core CFL, but then I don't know whether core CFL is regular detectable. And similarly, I have no idea how to prove that CFL of K, CFL sub K, both are regular detectable. What I have proven in this talk is the bounded, restricted version of the CFL of K and the CFL sub K. And concerning to the separation, I have no proof for the claim that the CFL I separate CFL comma CFL. So I'm seeking a collaboration from all of you. If you notice, if you just think about it this one, you don't know, you don't need to know a whole bunch of very complex ideas or complex notions or whatever. It's very simple. You just simply if you have a set, you just simply cut it, right? It's a very simple notion. But even though the notion itself is very simple, but it's kind of hard. From my point of view, it's very hard to find how to do it, right? So that you are very young, so that if you find if you think about this one for a while, then find the answer, please let me know. I'm going to write, we are going to write a very nice paper for this notion. Well, thank you very much for listening.
So one question is that so the separation property so this section property has some so what is the relation with the complexity of so deciding the language and so separability, detectability? Yeah, most of us are interested in computation. So.
Oh, I see.
Yeah. Okay.
Well, we know that the length of the inputs are very really important, but the length is not the only factor. So that we have to find some sort of structural property of the target language. So that's the most important thing. So maybe the computation, because the language, all the languages we have seen are defined by the computation model. So that the computation might play a very important role. But I have no ideas on how to find those properties.
Yeah, usually in this kind of theory, so we usually find that the class of so language which cannot be dissected, and so using that language as a core, we build up some systems. So my question is that whether such kind of theory can be established based on it.
At least there's a Boolean, well, the bounded version of the CFL K or CFL sub K are actually known to be detectable.
Right.
But I don't know how to expand this boundary into say CFL of K or CFL sub K, well, much beyond.
Okay. Any other questions? Okay, thank you.